Hello students, did you know that just like superheroes can swap out gadgets, molecules can swap out atoms to create something new and exciting? Today, we are diving into the world of amines. Imagine ammonia, the humble molecule with one nitrogen and three hydrogens. Now picture it going to a trendy makeover salon where one or more of those hydrogens get replaced by cool carbon-containing groups like alkyl or aryl groups. Voila! We have amines, those organic derivatives of ammonia with a twist. Amines come in three flavors based on how many carbon-based groups stick to the nitrogen atom: primary, secondary, and tertiary. Think of it as nitrogen hanging out with one, two, or three friends from the carbon club. Their general formulas are simple to remember. Primary amines have one R group and two hydrogens attached to nitrogen, written as RNH2. Secondary amines have two R groups and one hydrogen, so R2NH, and tertiary amines sport three R groups attached to the nitrogen, making R3N. Picture a diagram where a nitrogen sits in the middle with one, two, or three carbon branches, like branches of a tree. Why does this matter? Because amines aren't just chemistry class toys, they're everywhere, in amino acids that build proteins, in alkaloids which are bioactive compounds, and even in many medicines. So, from your body's building blocks to your daily medications, amines play starring roles. Let's talk names, the science of naming amines systematically, or as chemists like to say, IUPAC nomenclature. Think of naming chemicals like naming pets. You want a unique, clear name that everyone gets. In the IUPAC system, we take familiar alkane names, the simple carbon chains, and switch out the final E to amine. For example, if you have a molecule like CH3NH2, instead of calling it methylamine, it's called methanamine, simple but systematic. Now, what if a nitrogen has more than one alkyl friend, like in secondary or tertiary amines? Here, the IUPAC system gets fancy and uses N to indicate substitutions happening right on the nitrogen itself. So, if we look at CH3NHCH3, it's named N-methylmethanamine. The N-methyl tells us a methyl group is attached to nitrogen and methanamine is the parent. The longest alkyl chain in the molecule takes center stage as a parent chain, while other groups attached to the nitrogen get the N prefix. Aromatic amines, those with an amine group stuck directly to a benzene ring, get some special treatment. If the amine isn't the highest priority functional group, it's treated as a sidekick substituent in the naming. Imagine a diagram here showing line structures of these examples, straight chains with various alkyl groups, and how N helps keep track. This system avoids confusion and keeps our chemical names as clear as your best friend's nickname. Now, while IUPAC rules keep things neat and universal, chemists have loved their traditional or common names for ages, almost like nicknames that catch on easily. In the common system, you name the alkyl groups attached to nitrogen first, then just add amine to the end. So CH3NH2 becomes methylamine in common terms, quick and easy. If you have two or three identical alkyl groups hanging out, you use prefixes like di and tri dot. For example, having two methyl groups makes dimethylamine, and with three, it's trimethylamine. These prefixes really help count the substituents. When you have different alkyl groups mixed on nitrogen, you list them alphabetically, for instance, ethylmethylamine. For aromatic amines, like that classic benzene ring with an amine group, the common name steps in as aniline. Simple, right? Think of aniline as the celebrity nickname for C6H5NH2. Picture a table comparing common names and IUPAC names side by side. That's the perfect cheat sheet. Understanding both naming systems helps you talk chemistry like a pro and keeps you flexible whether you're reading a textbook or chatting with chemists who prefer the classics. Alright, let's zoom in on aromatic amines, the special case we just mentioned. Here, the amine group is attached directly to an aromatic ring, like benzene, making molecules super interesting and biologically active. In naming these, the amine group gets top billing. It's the highest priority functional group on that ring. So, all substituents on this aromatic ring are numbered around the ring with respect to the amine group, which sits at position 1. Imagine a benzene ring with the NH2 group at the top and numbers circling around clockwise. Substituents get prefixes like to chloroaniline, meaning a chlorine at position 2, or 4-nitroaniline, where a nitro group sits opposite at position 4, or 3-methylaniline, with a methyl group at position 3. The naming always reflects the placement on the ring relative to the amine. Visualize a diagram showing this numbered benzene ring with various substituents labeled. This priority and numbering system makes sure every chemist knows exactly where each group sits, like addresses in a well-planned neighborhood. Let's put theory into action with a solve example. That's where chemistry gets the most satisfying. Suppose we have a compound with the structure CH3CH2NHCH2CH3. Our task: find its correct IUPAC name. Step 1. Identify the longest carbon chain attached directly to nitrogen, that's the parent chain. Here, that's CH3CH2, an ethyl group. The other carbon-containing group attached to nitrogen is CH2CH3, another ethyl group, but since it's attached via nitrogen, we call that an N substituent. Breaking it down, one side is our equals CH3CH2, ethyl. The other R prime equals CH2CH3, ethyl attached on nitrogen. Putting it all together, the name becomes N-ethylethanamine. Picture a structure with labels showing the longest chain and the nitrogen substituent clearly marked to keep your mental map sharp. This simple rule, longest chain as parent and N prefix for nitrogen substituents, lets us name more complex amines with confidence. Now, what happens when amines share the stage with other functional groups that take precedence? Like when you have an amino group alongside a carboxylic acid or an aldehyde. In those cases, amines step down from their solo spotlight and become prefixes named amino dot. For example, in the compound 4-aminobutanoic acid, the carboxylic acid group -CU is the principal functional group, earning the main suffix, and the amino group appears as a prefix at position 4 on the carbon chain. Chemists follow a strict IUPAC order of precedence for functional groups to avoid naming confusion. Imagine a molecule where both Cu and NH2 groups compete. The Cu wins the suffix, and NH2 becomes amino. Precise numbering, called locants, gives each group a unique address, ensuring no misinterpretation. Picture a diagram illustrating a molecule with a Cu group and an NH2 group with their respective numbers and naming. So, while amines love the solo spotlight, they happily share the stage when bigger groups take lead. What if a molecule throws a party and invites 2 or more amino groups? We call these diamines or polyamines depending on how many NH2 groups are present. To name them, suffixes like diamine, triamine, and so on are added to the name of the parent alkane chain. For example, the molecule H2NCH2CH2CH2NH2 has 2 amino groups attached at carbon 1 and carbon 3 of propane. This molecule is called propane 1,3-diamine. In common names, it's simply 1,3-diaminopropane. The numbering is crucial here. Get it wrong, and you misplace the amino groups entirely. Consider a diagram displaying propane with amino groups at different positions, like 1,2-diamine and 1,3-diamine, to visualize the difference. Paying careful attention to the placement keeps the name precise and the structure unambiguous, chemistry's way of leaving no room for guesswork. To wrap up, let's remember the essentials of amine nomenclature. Primary amines have one alkyl group attached to nitrogen, written as RNH2. Secondary amines have two, R2NH, and tertiary amines have three, R3N. The IUPAC system names amines by replacing the final E of the alkene name with amine, turning something like ethylamine into ethanamine. When we have substituents on nitrogen, we use the prefix N to indicate these groups clearly. In molecules where higher priority groups like carboxylic acids are present, the amine group becomes a prefix amino dot. These rows work together to give each amine a unique, clear name that chemists worldwide can understand. So, whether primary, secondary, tertiary, or aromatic, these naming principles help you unlock the language of amines. Practice a few examples, and soon you'll be naming amines as effortlessly as chatting with friends. That's a wrap for today's lesson. Chemistry is much more fun when you can laugh and learn. See you next time.